It's unfortunate, but you'd be doing the world a big favor by dying right now. And while that might sound a little extreme, it's absolutely true from a thermodynamic perspective. You might not know this, but the only way that you were built up, the way that you were formed, was done so by way of breaking down something else around you. Why, do you say? The answer is entropy. It's the driving force behind all the chemical reactions in life, and also the idea of life itself. Knowing about entropy can not only help you appreciate the fact that you do exist, but it can also help you gain competitive advantage in whatever it is that you do. I will continue by discussing what entropy is, its effects, and finally its greater implications. But first, what is entropy? Entropy is everywhere. It's all around us. It's in this very room. But most quintessentially, entropy is disorder. Actually, it's the measure of disorder. But disorder can take shape in many different kinds of forms. It could be the mixing of two things. It could be the amount of space that something takes up. It could be the speed of random motions. It could be the order in which something is arranged. Or it could even be in the form of decreased chemical energy. But based on what we already know, we already see that nature favors disorder. For example, you'd be amazed to find that your room doesn't become a mess because you want it to be. It naturally becomes a mess because there are more ways for it to be a mess than there are ways for it to be clean. You'll oftentimes miss that three-pointer in basketball, not because you want to miss, but because there are more ways to miss than there are ways to make it. You'll fail that exam, surely, without studying, not because you want to fail, but because there are more ways to fail than there are ways to pass. And you'll be amazed to take an ordered deck of cards and throw them on the ground and pick them back up again to find them still in the same order. And likewise, salt dissolves in water, not because it's supposed to, but because there are more ways for salt to be dissolved in water, to mix in water, than there are ways for it to remain separated. And likewise, if we were to take this thing of Skittles here that are divided by color, separated by this cardboard insert, if we were to remove this and go ahead and replace the lid and shake this sucker up, we're going to find something, well, that we already expect. We're going to have a mixture of the Skittles. Now, nature doesn't know what color these things are, and it really doesn't even care. These things mix simply because there are more ways for them to remain mixed than there are ways for them to be separated. To overcome disorder, we actually have to do something. We have to put things in their place, just like you did to actually separate those things. We have to accomplish the improbable, and we have to organize at some level. And that's only going to happen when the energy put into organizing something overcomes the natural tendency to disorganize. However, in the chemical world, disorder doesn't just disappear or reappear. It actually comes from something else. And this only makes sense if you realize that there is a difference between the system and the surroundings. And when we talk about the system, we're talking about a part of the universe that we focus our mind on. And in this case, it's the contents of this tub. And the surrounding is everything else around it. Now, based on what we already know, you might already know this, you're made from about carbon, heavy metals, oxygen, and some other atoms of sort. And if you were to go ahead and take that entire content and throw it into a corner somewhere, you'd be amazed to actually come up with Bethany over here, for example, or Dylan. I mean, what are the odds of that? I mean, that is a high level of organization. So how did that disordered pile, make you? Well, that happened by way of disorganizing something else around you to go ahead and organize yourself. But how did it move? Well, it moved in the way of heat. Now, heat causes disorder because it increases the motions of things. And this only makes sense if we realize that in the chemical world, things are already moving. For example, the molecules of gas in this room, they're bouncing across the walls about 50,000 times a second. Likewise, when you look at a glass of water, for example, these molecules are not sitting still inside the glass. They look like they are, but they're actually swirling around extremely fast. That's why it's in the liquid form. But when we talk about disorder, we're talking about how fast something is moving. So, whereas this is disorder, this is absolute chaos because it's occupying more positions per increment of time, which means that it can see more possibilities in its positions at any point, which therefore increases its actual state of disorder. So, based on the chemical world, we see that things are always moving, and that's why when you heat something up, it determines how fast something is moving because it actually makes it move faster. Faster something's moving, the more disordered it becomes. So likewise, if we were to take this glass of water and heat this solution up, you'd find that the molecules start circulating around faster and faster. They bounce around until finally they overcome their intermolecular forces that are holding them together, and eventually they'll fly right on out of the cup in the form of what we call steam. That's what happens when we go ahead and heat something. Now let's say that if we were to cool something down, all we're doing is we're taking the heat from inside of this glass, for example, and if we were to go ahead and suck that out, then we would actually slow down the molecules to the point where they'll go ahead, they'll slow down, and finally they will stop. And at that point you've achieved an ordered crystal. And when you have an ordered crystal, it's like looking at a 6-lane highway in rush hour traffic. All the cars are pointing in the same direction in their lane. Notice how this kind of level of organization isn't very probable, and really it shouldn't happen, but it only did so when we actually took out all the heat that kept those molecules moving. Well, that's basically what we're talking about when we say that disorder moves elsewhere. We took out the heat, which went ahead and increased the disorder for the surroundings. What we see here is that entropy wins at cold temperatures. As Zumdahl put it, a cold room is kind of like a poor neighborhood. And if you were to go ahead and bring something hot into it, it's kind of like something that's going to go ahead and get robbed. So when you go ahead and put water in a cold enough environment, water will not try to actually mix. It will actually end up getting all the heat sucked out of it that keeps those molecules moving. And that's why you'll go ahead and form that ice crystal. And that's only going to happen when you go ahead and increase the disorder on the outside enough for that to happen. Ordering to this degree, it actually takes a lot of energy. And so it's just like that robber, it's got to actually suck everything out of it to go ahead and make that happen. And that's why water freezes at 32 degrees. It's because that's how cold it has to be outside to go ahead and suck out all the energy that keeps all those molecules moving. This brings along some interesting implications. This is what it comes down to, guys. Entropy is the real driving force behind all interactions that we see. So while it can't be destroyed, it is also always increasing. Let's just say I take this glass of water and I put it in the freezer. The freezer doesn't work by doing anything magic. All it does is it takes the heat from inside this glass and just puts it on outside. But you'll find that there was more heat that was kicked out outside than what came from this glass, because meanwhile you've got this power plant actually powering the freezer, which is kicking out thousands of kilojoules in energy and excessive heat from burning coals and fossil fuels. So that's also increasing even more entropy in the universe. So what we find is that while the entropy for the system and surroundings remains about equal in exchange, the entropy for the universe is always increasing, because there's always more heat getting kicked out than what heat actually went into anything. And so what we find here is that releasing energy to achieve order somewhere actually results in energy in a less usable form. When your car burns gas, it basically takes energy in a chemical form, in the gasoline, and it kicks it out in the form of heat and low energy molecules. And reversing this process takes thousands of years, and hence our upcoming dilemma once we burn all of our fossil fuels, because that kind of process just can't be remade in any time that would be feasible to our needs. So what we find here is that in essence we are doing the same thing. Just by you being formed, there's no way it can happen if you did not actually release enough heat to go ahead and allow that level of order in your system. And so reversing this process even takes a lot of time, and that's even after you die. So don't go kill yourself or anything, but do realize the fact that you do exist is quite improbable, and it overcomes a lot of odds. Whereas nature overcomes its natural tendency for disorder through the exchange of heat, you overcome the natural tendency for disorder through the exchange of practice and hard work. Good or bad, either way, this helps you see that life is just full of possibilities, and all you have to do is check on them. And that's what the exchange of entropy is all about.